So it's a really great pleasure to be here. I'd like to thank the organizers for inviting me. And also I apologize when the organizers asked for the title. I wasn't exactly sure what I'm going to talk about. So, this new title, so I've done something violent to the original title. I cut it into 3 pieces and kept 2 out of the 3 and added something else. But hopefully this is the same spirit as fractionalization. Okay. So I'm going to talk about basically the fractional quantum Hall effect, but at the zero magnetic field. And we will see that this phenomena occurs in topological bands due to magnetic ordering. So there's magnetism and topology. So this work would not be possible without my collaborators. I started in collaboration with Zhen Bi, who was a student here and then became a postdoctoral fellow at MIT. And the work I'm going to highlight today are done in collaboration with Dynamical, Yang Zhang, and Valentin Krappel. Chutov and Yang now faculty at Stanford and the University of Tennessee, respectively. Valentin Krappel, my former student, has joined Flatiron as a postdoc. And the recent work is done with the new generation of students and postdocs, Aidan Reddy and Hugo Onishi, my students who are both here. Faisal is an undergrad joining Berkeley for a PhD. And also I'm going to mention recent works with Nishaga Paul, a student. Howard Goldman is our more postdoc fellow. And I won't have time to talk about some recent direction I'm quite interested in, the neural networks. But Di Luo, my collaborator, is actually here as well. We've benefited enormously from interacting with experimentalists, starting from collaboration with the Cornell group. You've heard Ping-Pan Max talk this morning. So I got interested in these semiconductor Moiré systems based on my interaction with him from 2019. And the experiment I'm going to talk about today involves collaboration with Xiaodong Xu's group at the University of Washington, Seattle. Okay, so let me start by talking about the Hall effects, the electrical Hall effects. And as we all know, the Hall effect is an important phenomenon in condensed matter physics, and it has led to many important advances in our field. In particular, in the 1980s, it was found that the Hall effect in 2-dimensional electron systems in the high magnetic field can actually become quantized. The Hall conductance can be an integer or a fractional version of E squared over H. And this unexpected discovery has revolutionized our field in many ways. And then starting from 2013, another kind of quantum Hall effect has been observed, but now in a zero magnetic field. And they only occur in special quantum materials with special topological properties. And obviously, the development of a Hall signal requires time-reversal symmetry breaking. And in this zero field quantum Hall effect, this occurs through magnetic ordering that spontaneously break time reversal symmetry. And for that reason, the integer quantum Hall effect at zero magnetic field is known as the quantum anomalous Hall effect. And more recently, very recently, the fractional version of this effect has been observed according to several experimental reports. So let me briefly, for this audience, let me very briefly review the path to the integer quantum anomalous Hall effect, okay, discovered 10 years ago. So sort of starting from the pioneering work of Thouless and Haldane, it was realized that the Hall conductance in the 2-dimensional insulating state is actually a topological invariant. So in the case of the 2-dimensional electron gas in the high magnetic field, this integer is simply the number of occupied lambda levels. But more generally, in matter principle, one can have a system without external magnetic field or without lambda levels. And in this case, the integer quantum Hall effect comes from a fundamental topological invariant associated with the electron wave function of the occupied bands. And it was thought to be a theoretical curiosity for a long time, but eventually this was realized in magnetic doped three-dimensional topological insert films. And I just want to briefly show here that along the way, right, many new ingredients were found. For example, the three-dimensional topological insert played a key role. In these materials, the bulk is insulating, but the surface has spin helical electrons forming a massless direct cone. An example is this bismuth telluride. And when time-Rousseau symmetry is broken, these surface direct cones are protected by time-Rousseau symmetry, by Kramer degeneracy. So when time-Rousseau is broken, it leads to a half-integer quantized Hall effect on the surface. When we combining the top and bottom surface, when the magnetization is pointing along the same direction, one can get this integer quantized Hall effect in this film of a 3D topological insert. And the way to achieve this was proposed by computational physicists and theoretical physicists is to introduce magnetic dopants, and in this case, the exchange field from the magnetic dopants break time-Rousseau symmetry and open up a gap on the TI surface states. So this is somewhat like a kind of a marriage between magnetism and topology, and it's a little bit like a forced marriage, right? So the TI film provides the topological direct states, while a magnetic dopants provides magnetization. And but it worked. This is the experiments showing that at the zero field, the Hall conductance becomes quantized at low temperature, and the material is chromium doped bismuth telluride. Okay, now let me move on to the more recent. Before moving on to the recent stuff, let me just point out that if you compare the Landau level physics and the magnetic topology inserts, there are many differences. So in the case of the magnetic TI, we don't have any flat band. Bandwidth is in the order of electron volt. However, there's one common aspect. The key physics of both systems is actually governed by long wavelength continuum theory. In the case of the conventional quantum Hall system, it's described by a 2D electron gas coupled to a magnetic field. This can be realized in principle, any semiconductor, silicon, germanium, gallium arsenic. We don't worry about the individual atoms, individual crystal structures, but the low energy physics is that of a 2D electron gas. In the case of a magnetic topology inserts, again, the bulk can be complicated, but all we care is that there exists massless direct fermions on the surface. So we're dealing with a direct electron gas. So both long wavelength continuum systems, the physics does not depend on the details. Okay, then now let me switch to the more recent developments. These are, again, based on low energy, long wavelength physics in an effectively continuum medium. And so this sort of it was predicted and then discovered in 2018 that magic angle twisted bilayer graphene is a great example of the Moiré materials. And in these Moiré materials, you have a large unit cell, super lattice unit cell with a wavelength on the order of 10 nanometers. This is actually comparable to the magnetic length at say 10 Tesla. So somehow this length scale always seems magical to me. And so when you have this periodic modulation, again, one can get mini bands, right? Instead of thinking about the large bandwidth dispersive bands in the monolayer graphene on the order of 10 electron volt, you fold this Brillouin zone into mini Brillouin zone, you introduce Bragg scattering, and you can open up a super lattice induced gaps, and then we end up with a mini band, right? Very similar to the magnetic Brillouin zone. Initially, the excitement about the TBG comes from the discovery of superconductivity and correlated insulating states. But then in the 2019, I remember attending this rapid response workshop at KITP. It was reported that from the David Gordon's group that actually when the TBG, magic angle TBG is aligned with boron nitride substrate, a very large anomalous Hall effect appears, okay, large. And later experiments from here showed that in certain devices, at least, this Hall effect can become actually quantized. So this is the integer quantum anomalous Hall effect. Okay, so this phenomenon is remarkable, I think, because after all, we're dealing with carbon, does not have any magnetic atoms, and yet it shows ferromagnetism that are purely of orbital origin, right? And unlike unlike the magnetic doped topology insulator case, here magnetism and topology, they really come together. They both arise from the same set of itinerary electrons. Right? Those electrons are low energy that form topological bands are the same as those that give rise to spontaneously valid polarization and magnetism. Okay, so this is, instead of a forced marriage, this is more like intimate partners. Okay, all right. So and it was quickly understood that the essential physics is that you have narrow Moiré bands, and these Moiré bands at the different values k and k prime, they have opposite Chen numbers, presumably coming from alignment with HBN that breaks the twofold rotation symmetry that generates barrier curvature, and etc. So there was a lot of excitement that finally we have a system which seems to share many similar features as lambda levels, but now this can potentially provide a route to quantum Hall effect and perhaps even a fractional quantum Hall effect at a zero external field. So, so basically, we know that in the case of lambda levels, what we to look for the fractional quantum Hall effect, we can look at the fractional fittings instead of integer fittings. And indeed, there are many early theoretical proposals, ideas about how fractional quantum Hall effect can occur beyond lambda levels. And in particular, there have been in around 2011, there are many studies of fractional quantum Hall effect from flat or narrow Chen bands in these toy lattice models, and they demonstrate, at least as a matter of principle, indeed this can happen. And some of the authors are in the audience here, Dongnan Shen and Shankar Sama. And so now that the experiments, 2019 experiment, showed that indeed this twisted bilayer graphene magic angle TBG can show large or quantized anomalous Hall effect. So the natural question is, at partial fitting, can this lead to the fractional quantum Hall effect at zero field? And unfortunately, for the case of TBG, it still hasn't worked. And in fact, fractionally quantized Hall effect at zero field has never been observed until now. Okay. And the new system that I'm going to talk about is not graphene, but these semiconductor transition metal dichalcogenides with the formula of MX2. Examples are tungsten diselenide and molybdenum ditelluride. And as you heard from Bai's talk this morning, these are basically has a honeycomb structure, but with different sublattice potential difference. So the low energy states are actually in the metal atom, which form a triangle lattice. And the key electronic property is that the valence band top is at the k and k prime, the two values, like in graphene. But because of the large atomic spin-orbit coupling, the states at the band edge are spin polarized. Spin up in k values, spin down in k prime value. They form time-reversed partners. And unlike graphene, which has a zero mass, it's a Dirac particle, here we're just dealing with a simple Schrodinger particle, but with a very large effective mass on the order of a free electron mass. So this basically is a 2D electron gas with strong correlation, so in monolayer form. So the physics of these TMDs become much richer when the Moiré structure is formed. And one way is to take two different TMDs with different lattice constants and stack them together. But I'm going to focus on taking two identical layers of TMDs rotated relative to each other by a small twist angle. This is called twisted homobilayers. And I think the hero of this story is really Alan MacDonald. Many of you know that he discovered this magic angle in TBG, but maybe not everyone knows that he also wrote down the two foundational works in the study of the TMD Moiré superlattice. So the 2018 PIL paper, he and Fengchen Wu and collaborators showed that if you take a heterobilayer of TMDs, this could be a good platform to search for a strong correlation Hubbard model physics. And in the following year, 2019, Alan and Fengchen Wu and collaborators showed that twisted homobilayer TMD have topological bands, so that it becomes a time reversal invariant topological insulator when these bands from two values are both filled. Okay. And my group has been working on the TMD for quite a while, starting from 2019. So, so Alan's vision has kept me busy in a happy way. So we worked on various aspects of these TMDs, and some of them you may have heard from this morning Kim Max talk, for example, the spin-phonons. And today I'm going to focus on this quantum non-Hall states, both integer and fractional version, and they are intimately tied to ferromagnetism in topological bands. Okay, so the two groups predicted the existence of integer and fractional quantum non-Hall states in homobilayer twisted TMD. One is from Kai Sun in University of Michigan in collaboration with Shizhen Liang at Los Alamos, and the other is from my group at MIT in these two papers. Okay. So let me very briefly tell you the essential, the origin of band topology in this system. That's pointed out by Alan. So this is a Moiré superlattice structure, and you see that within the Moiré unit cell, there are different stacking regions. The M region, where the metal atoms are on top of each other, and the MX or XM region, where the metal atom of one layer is aligned with the Dichalcogenide atom on the other layer. So let's think about this sort of electronic structure in a local way. There's a periodic potential, like electrons experience on each layer that has a periodicity of the Moiré superlattice, which I call delta T and delta B. And then in addition, there's an interlayer tunneling between the two layers. Now, the key feature is that this interlayer tunneling is complex valued. So we know complex numbers are needed to produce barrier curvature, right? And the reason is that remember that the top of the valence bands is at the K point in the monolayer Brillouin zone, and the K point carries a large crystal momentum. So if you look at the block wave function in real space in each layer, the wave function has a periodic variation of the phase on the atomic scale. So here the arrows represent the phase. And when you take a second layer and lay it on top of the first layer, so in the MM region, the interlayer tunneling all add up constructively. So you get interlayer tunneling is real. But when the second layer, the metal atom is exactly at the center of the hexagon of the other layer, this is exactly what happens in the MX region, then the tunneling between metal atoms on the two layers, the three tunneling paths interfere destructively, and that leads to a vanishing interlayer tunneling at the MX and XM regions. So for that reason, we can see that this continuum model for twisted homobilayer takes a very interesting form. Okay, so here it's a 2x2 matrix in the space of the layer degrees of freedom. So we have kinetic energy on each layers. We have a periodic potential on each layers, delta T, delta B. And then the interlayer tunneling is an off-diagonal term, which is complex. So combining all these three potential terms, they can be written in a unified way using a Zeeman field notation. So think of the layer as a pseudo-spin, and then this homobilayer system can be viewed as a pseudo-spin 1/2 particle moving in a periodic Zeeman field. And this Zeeman field actually formed a skyrmion texture in real space, right? Because the XY component is complex and it shows windings and vanishes, and the Z component oscillates between positive and negative. And we also know that in the case of the skyrmion lattice, the skyrmions create an emergent magnetic field, in this case corresponding to 1 flux quantum per Moiré cell, and this is why we get topological bands. Okay, so in this case, one thing I should mention is that the whole system still is time reversal invariant. There are two values, K and K prime. So the pseudo-magnetic field from the skyrmion lattice is exactly equal and opposite. So the Chen number of the two spin states, the two values, are also equal and opposite. So the whole system preserves time reversal symmetry. So at the complete band filling, we get a quantum spin Hall state, not a quantum non-Hall state. So, so we looked at what happens when you have these bands are partially filled, in particular, for example, when it's half filled, meaning that one electron per Moiré unit cell. And the experiments from Columbia group initially showed that there's indeed an insulating state, but there are absolutely no sign of topology. And we understood that this is because the bandwidth is relatively high. So instead of fully polarizing all the electrons into one valley, it's energetically more preferred to form an inter-valley coherent state because of the two valleys has the opposite number. There's no net topology left. So in order to achieve a valley polarized quantum non-Hall state, we need to look for smaller twist-angles with a smaller bandwidth. So this leads to our work with Christoph Debicol, Yang Zhang, and Valentin Krappel. So here I'm showing the Moiré band structure as a function of twist angle. And as you can see that over quite a large range of twist angles, the topmost valence band is quite flat. It has a narrow bandwidth, less than 15 millielectron volt. So basically we see that narrow topological bands appear without fine-tuning the twist angle. As long as twist angle is smaller than, say, 4 degrees, it works. On the other hand, we also know that something's very special. At a particular magic angle, the band is not only exceptionally flat, but also the barrier curvature is particularly uniform. Right? So this, again, reminds us of Landau level physics. So by doing the self-consistent mean field calculation, we showed that at the filling of 1 electron per unit cell, there's a rich phase diagram, especially tunable by the electric field that induces potential difference between the two layers. And in addition to the valley polarized, spin polarized, valley polarized quantum non-Hall states, there are also other magnetic insulators. So it's physics very rich. Now, for this talk, if you want to think about analogy with Landau levels, we can see that, for example, in twisted WSC2, we can see that the topological gap can be, the gap between the first and second band can be on the order of 5 millielectron volt, which corresponds to magnetic field 20 Tesla. And in monolayer WSC2 with such a large magnetic field, both integer and fractional quantum Hall states have already been observed. So the question is now, in this twisted TMD homobilayers at zero field, can topological bands play a similar role as magnetic field and generate fractional quantum Hall states? So with Valentin Krappel, we studied this problem using exantization, and I don't need to go through all the details. All I want to say is just we find that over a wide range of filling range, below filling factor 1, all the way to below in half filling, below 0.5, we find that the spontaneous valley polarization occurs and is complete 100%. Okay. This means that at generic fillings, the system should be a metallic state, which shows an Anomalous Hall effect because of the barrier curvature in the spin valley polarized band. And at the specific filling factors, for example, like 1/3, exantization study shows the ground state is 3/4 degenerate, and when we do the usual test, we find that it can be either fractional quantum non-Hall states or competing CDW states, depending on details. Okay, so now very recently, there's some multiple experimental groups reported evidence of the quantum non-Hall states, both integer and fractional version, in these twisted TMDs, in particular this twisted MOT2. I'm not going to be able to go through all of these. I'll just show you the transport results from Xiaodong Xu's group, which we collaborated with. And this is the experimental phase diagram. These are dual-gated twisted MOT2, and the x-axis is the carrier density, the y-axis is the electric field. And you can see many features in the RxX and RxY. There's quantum Hall states, basically a filling factor both 1 and 2/3, as well as 3/5, as we will see in a minute. So I'm going to mostly focus on just the states appearing at the zero displacement field. So at the filling of 1 charge per unit cell, you can see that the Hall conductance is quantized into an integer, e squared over h, and it persists over a range of electric fields and until it dies. And in the quantum non-Hall region, the thermal activation gap can be as high as 30 Kelvin. let me just skip this. In the 2/3 filling and 3/5 filling, we see that the quantized Rxy with corresponding Chen number corresponding to -2/3 and -3/5. Okay, so in this case, again, this plateau persists over a range of displacement field, and the energy gap is on the order of 20 Kelvin. 100 millikelvin. Measurements are done at 100 millikelvin. Okay, very recently there's another group from Shanghai Jiao Tong University that also observed similar features. Okay, so in the last 5 minutes, okay, I'm going to talk about our current theoretical understanding about experimental results. And this work is largely driven by my student Aidan, who is here in the audience. He did an enormous amount of numerical study and theoretical analysis, and that's what I'm going to report here. So again, the first thing is about magnetism, right? The system consists of 2 spin-degenerate bands, and only when electrons are spontaneously spin-valley polarized, we can expect any anomalous Hall effect. So so these are exactization studies, and indeed we found that out of a whole range of fitting factors, the ground state is fully spin polarized, and the x-axis is the filling factor, the y-axis is the spin gap, the Magnon gap. Because of the 2 spin state bands have opposite barrier curvature, the system has no SU2 spin rotation symmetry. It only has a spin U1 symmetry. And for that reason, the Magnon spectrum is not gapless, but has a gap. And you can see that the Magnon gap is largest at integer filling when the system is in quantum non-Hall states, and then generally decays. But interestingly, at the fractional quantum non-Hall states, at 2/3 filling, you can see a small enhancement of the Magnon gap, and that is consistent with the experimental observation of enhanced ferromagnetism at these fillings, which I don't have time to show you. Okay, so once we are in the spin polarized regime, we can study the phase diagram as a function of filling factors to ask, as a function of filling factor, what kind of states do we get? And it turns out that the phase diagram depends quite a bit on the twist angle. There is a particular twist angle, this magic angle that I mentioned, which is where the barrier curvature is most uniform. And in that case, we see features that are remarkably similar to that of the lowest and Lambda level. We see a whole sequence of fractional quantum non-Hall states, and these plots show the charge gap. The charge gap decreases as you go to half filling, and right at half filling, we get the composite Fermi-liquid state, but now at the 0 field. On the other hand, if you go to a larger twist angle, then the phase diagram deviates quite a bit from that of lowest and Lambda level. And the first thing you may notice from the charge gap plot is that it's strongly asymmetric with respect to half filling. And most striking is that comparing 1/3 and 2/3, fractional quantum Hall states appears at 2/3, but not at 1/3. Instead, a charge density wave, an in-swing charge density wave state appears 1/3. Okay. Also, over a range of filling factors from 2/3 to 1, what we found is the system is actually a Fermi-liquid state. Okay, Fermi-liquid state with spontaneous spin polarization, and therefore it shows anomalous Hall effect, unquantized anomalous Hall effect. So by itself, the Fermi-liquid is not particularly interesting, but this is something that is completely absent in the Lambda level case. In the Lambda level, the kinetic energy is completely quenched, but this is not the case here. Actually, we get a coexistence of fractional quantum Hall-like states, Fermi-liquid states, the non-Fermi-liquid, the composite Fermi-liquid states, and charge density wave states. So it's quite a rich phase diagram. I'll show you. Yeah, I'll show you in a minute. Yeah. Okay. So let me very briefly tell you a little bit about this composite Fermi-liquid state. As you can, basically, the one way to summarize this phase diagram is the following: that near the magic angle, the physics is remarkably lowest and Lambda level, like across a whole range of fillings. But as we move away from the magic angle, regions near the half filling is the most lowest Lambda level like, while regions away from half filling become less and less Lambda level like. Okay. So therefore, somehow there's something special about half-filling. Okay. So in the case of half-filling, these are the many-body spectra. And all I want to say, just if you look at the ground state degeneracy, this is all similar to that of the lowest and long level, done on the same cluster geometry. And on the bottom panel, I've shown you that the momentum distribution function n of k, okay, the electron momentum distribution. And despite the system is metallic, the electron distribution function is quite uniform in k space. So this is, again, it doesn't show any sign of a sharp Fermi surface. So that's, again, consistent with a non-Fermi liquid state. And this momentum distribution function, in principle, can be measured by nanoampers because this occurs now at the zero magnetic field. Also, this composite Fermi liquid state, because the gapless degree of freedom are not the bare electron, if you do tunneling experiments, it will see a suppressed densive state at the Fermi level. So there should be a pseudo gap. It is known from the quantum Hall community, long known, that one of the ideal way to probe the composite Fermi liquid state is through the geometric resonances, right? To probe the Fermi surface of composite fermions, one can introduce an external periodic potential, and when the sectional resonance of composite fermion matches that of the periodic superlattice, one get the resistance oscillations. And the physics here is that in both cases is that as we move away from half-filling, the composite fermion experiences an effective magnetic field, okay? Effective magnetic field. And in the case of lambda levels, one can move away from half-filling typically by changing the magnetic field. But in our case, all these states occur at zero external field anyway. So here, if we just change the density of the carriers away from half-filling, we would expect resistance oscillations. So this is something we call intrinsic commensurability oscillations. And if we look at the resistance extrema, plot 1 over delta n, it will fall into a straight line with a spacing that is 2.3. Here, delta n is in units of the basic filling factor. Yeah. Okay, so I'm almost done. So about the question, how much is observed? So this is the experimental phase diagram. And you notice that in this region between 2/3 and 1, right, the Rxy become very small, but it's not zero. In fact, in this region, Rxy is comparable to Rxx. So this is the region that we believe is a Fermi liquid state with breaking time rules of symmetry, showing an unquantized anomalous Hall effect. On the other hand, you see that at half-filling, Rxy is actually very close to 2 h over e squared, or in other words, sigma xy is very close to 1/2 e squared of h. So this is consistent with the composite Fermi liquid state. Also, notice that here the Rxy is much bigger than Rxx, right? And also from the optical measurement at this half-filling, the system seems to be compressible, does not have a gap. And likewise, you see that in the Rxy plot, there's no plateau at filling factor 1/2, while there's at least a weak plateau around 3/2, around 2/3 and 3/5 filling. Okay, so I've only basically showed you our calculation at the zero displacement field. The phase diagram is very, very rich if you also take into account the electric field. So many phases and phase transitions are possible. Okay, so let me just summarize that basically over the last maybe 1 or 2 decades, advances in topological materials, Moiré materials, has actually led to the observation of integer and fractional quantum Hall effects now at zero magnetic field. And despite all the differences, all these systems, lambda levels, magnetic TIs, and twisted TMDs, are described by long wavelength continuum theory. And as a theorist who does modeling, I find this very appealing. I'm running out of time, so I'll just leave the outlook slides here. Thank you.
Thank you, Liang, for a beautiful talk.
Liang, I have a couple of questions since you justifiably drew all the analogies with fractional quantum Hall.
Yeah.
So in the fractional quantum Hall, when you do numerical work, we do many things, just getting the gap and those, and scaling is just one part of it. It's of course, 50-year-old industry. We look at overlap with candidate wave function. We look at entanglement spectrum. We look at degeneracy. And most importantly, we calculate the activation gap and compare that with experiment also. So I have not followed the work too much. Can you tell me which of those things has been done? How does the gap compare with the experimental gap? Did they measure the gap? I mean, I have many questions, but let's just
sure. So I didn't show you all the calculations we have done, meaning Aidan has done. No, this is for example, right? This is a many-body spectrum at 2/3 filling and 1/3 filling at the different twist angles. When you thread the flux, you twist the boundary condition, you see that these states permute. This is the key signature of the fractional quantum Hall states. And also here, what we are plotting here is the gap in the neutral sector, neutral gap as a function of twist angle, and for different interaction strength. And you can see that at 2/3 filling, the fractional quantum Hall states survives over a large range of twist angles. That's actually consistent with the latest experiment. So the Sheldon-Schultz experiment is only looking at a one twist angle, 3.7 degrees. The Cornell experiment actually look at a whole range of twist angles. So they find the fractional quantum Hall at least in the range of from 2.5 degrees to 3.7 degrees.
So in the context of this, just two quick follow-up. One is that did you do scaling as one of our system size to see what the gap is? I mean,
I think Aidan is here. Aidan, may have tried a little bit. Yeah. Feel free to,
Okay, I haven't done a very systematic scaling analysis of like the part neutral gap at say for a factor of 2/3 or 1/3. But just anecdotally, on different system sizes, I've noticed that at a given twist angle, it stays around 2 MeV, as is shown in that plot here.
It will be helpful to do the scaling because in a finite size system, you always have a gap. So
yes.
And the second thing is that did they measure the activation gap? How does the activation gap compare with your calculated
right?
gap?
So for example, right at here at 2.7 3.7 degrees, this gap is only order about like a 2 milli-electron volt. The activation gap is 20 Kelvin. So
one is 22 Kelvin, your gap, and what is the experimental gap?
The gap in the ED that I just showed you using a certain dielectric constant, which we believe is maybe reasonable, epsilon equal 5. The gap is in 2 milli-electron volt, about less than 2 milli-electron volt. Experimentally, the activation gap is 20 Kelvin. 20 Kelvin, yeah. So
20 Kelvin. The activation gap is 20 Kelvin. 20
Kelvin, yeah. So it is larger than gallium arsenide because of dielectric constant, right? Because in these systems, epsilon is about about 4 or 5 instead of 14. Also, the Moiré period is shorter. The Moiré period at 3.7 degrees is shorter. It's I think less than 10 nanometers. Yeah. Yes.
So what's the anomalous composite form? So is there a flux attachment picture for the anomalous composite fermi-liquid state, for example? I mean, this is momentum space topology.
Yeah, that's a great question. So in the case of the composite fermi-liquid state, right, the usual picture is that if you work with a full Hilbert space, you can do flux attachment, right? If you instead of focusing just within the lowest echelon level, right, you can do flux attachment to understand the composite fermion picture. Here there's no external magnetic field, right? So obviously that picture doesn't really quite work. What I can say, the best I can say at this point is just that one can again look at the projected Hamiltonian. Right? In the case of lambda levels, we can look at the Hamiltonian projected into the lowest echelon level. Here we can look at the Hamiltonian projected into the lowest Moiré band. And in fact, I should mention that all the ED calculations are done with the band projected model. And we are fully aware that multi-band effect may be important. That's also future study. Now, within the level of projected Hamiltonian, right? Then if the wave function of this topological band sufficiently resembles that of the lowest echelon level, then we expect to arrive at similar phases, right? Including the fractional quantum Hall states, including the composite fermi-liquid states, and that appears to be the case around 2 degrees. Now, if you move away from 2 degrees, as I showed you, the phase diagram becomes different, right? How do you understand this? Beyond numerical calculation, these are all interesting questions. Yeah. So I'm not sure I've really answered the question, but I'm just telling you the current status in our understanding. Yeah.
Other questions?
So there's this giant gap in the experiment, and the experiment is done in 30 millikelvin, as far as I understand. That should give super precise quantum Hall quantized values for the conductance.
Sorry.
So I'm asking how quantized
How quantized? Oh, yeah.
was the conductance?
Right, okay, yeah. I think I know the answer. Right. So at integer filling, the deviation from the quantized value is less than 0.1%. At these fractional fillings, the deviation is about 1% in the UW experiment. Yeah.
And wouldn't you expect less if there's truly a gap of 20 Kelvin?
Would I expect less? Well, actually, with this level, for experimenters working on 2D materials, they will find this quite remarkable already. Yeah, the sample is not uniform at all. The calculations done for clean systems. There are a lot of disorders.
I guess my question was what really this gap means. What this 20 Kelvin gap really means. Is it?
It's activation gap. That's all I can say. Mm-hmm. It was measured in devices, in twisted MOT2 devices in 2 devices. And this activation gap is 20 Kelvin. Yeah. Now, of course, there are disorders present in the system. There are twist angle inhomogeneities. All these factors are there. So,
okay, thank you.
I think at this point, making a quantitative comparison is maybe a little bit too ahead of time.
I think it's very impressive to have these gigantic gaps.
Yeah. I mean, that I think just follows from the rough energy scales. If we think about E squared over epsilon LB. Right, replacing that with E squared over epsilon AM, the Moiré period. The dielectric environment is different. Epsilon is smaller here, interaction is stronger. The Moiré period is relatively small. Yeah. I think at this point, just a very rough.
Graphene fractional quantum Hall gaps are very large for the same reason.
Yeah, for the same reason. Yeah, absolutely. With magnetic field, of course.
Yeah, no, I mean real fractional.
Yeah.
I have an experimental question or materials question. Maybe you said it early on. How hard is it to make the samples in the sense of like once they have the procedure, are these samples unicorns? They were just the only ones that showed this effect, or now that's it's hard to get it back, or they can do it every time now, or half the time?
Again, I'm not sure I'm in a good position to answer this question, but I can just tell you what I learned from my collaborator, right? That in the UW group they said there are 2 devices that show this, and then there's a recent experiment from Shanghai Jiaotong University. Yeah. Independent lab making their own devices, and you can see that here, of course, the data is perhaps not as great. At zero magnetic field, you see the rho xy, it's close to quantization value, but rho xx is also very large. Yeah. Then applying a 0.3 Tesla or 0.2 Tesla magnetic field, rho xx becomes much smaller.
We don't know. It's 2 out of 5 or 2 out of 1,000.
That I don't know. Yeah. I mean, it's clear that these are all early. Well, we are in the early days. Yeah. For this one. That's for sure. Yeah.
Yeah, beautiful talk. It's all very impressive, particularly the experimental advances, but also just the understanding the theory already at that level so quickly.
Coming up.
Yeah, sorry. I forget the expression. There's always a little honey before, anyway, before the sting. So the question I have, I guess, is, since everything seems to be happening within the background of ferromagnetism, is there theoretically even any state here which is kind of new from the fractional quantum Hall point of view? Apart from that, it breaks time reversal spontaneously.
Yeah, certainly in terms of topological order, right? So all these states, we believe that in terms of topological order, it's the same. The states observed so far is the 2/3 sigma xy equal 2/3 state at 2/3 spinning, sigma xy equal 3/5 state at 3/5 spinning. I mean, in terms of topological order, it's the same as that for the lowest echelon level. And Aidan compared the many-band spectrum, and they find that ground states all lie in the same momentum sector as that of the lowest echelon level. Yeah, so in this system, I think so far, these fractional states are the same as lower echelon level. Now, on the other hand, I can advocate that beyond the fractional states that are most interesting, perhaps there are outliers, right? There are coexisting other phases. From a liquid phase, we have charge density wave states. How these states compete with the fractional quantum Hall states, these are all open questions.
But an anomalous Hall Fermi liquid is just a ferromagnetic. It's just a ferromagnetic metal.
Yeah,
right.
But it shows a non-Hall effect because of barrier curvature in the bands.
So do ferromagnetic metals.
Yeah. Agreed. Agreed. But then we can ask, what about these phase transitions, like flying electric field?
Yeah, no, sure. Just from a theoretical point of view,
so far the fractional states are the same.
Yeah.
Topologically the same. Yeah. Except that it requires spontaneous ferromagnetism value polarization. Yeah. But this does not have to be the case. One thing I want to highlight is that this does not have to be the case in future systems. In fact, there are many possible ways to get quantum Hall effect without full value polarization, without even invoking topological bands, right? And also including the fractional states. Things like couple wire construction, and for example, we actually explored the case of integer quantum Hall effect in systems with non-collinear spin polarization. Not just fully value polarized, but involves both partial value polarization and this inter-value coherence. So I think these are all, interesting open questions. Yeah.
Thanks.
Yeah.
Okay, so if there are no more questions, let's thank Liang again.